I'm very proud of you guys.
Thank you.
I heard that when you were gone, you made Miss Katoom do this. Is that true?
And she loved it.
She was surprised that it worked.
Hilarious. Coming from the crowd, it's great. So I'm hoping that you guys are building up a certain level of confidence with electrochemistry. It is not a super easy concept. It builds off of redox. So if you are not comfortable with doing redox, remember there is a POGO activity specifically on oxidation number. So if you're like, I don't know how to look at a molecule and determine oxidation number, the POGO activity is there for that. So we're not going to do that in class because that was Gen Chem 1 and we're trying to keep moving. The last 2 days of class, my goal is to try to tie a lot of things together from this semester. So we're going to be tying together Gibbs free energy, equilibrium constant, Q, change in enthalpy, change in entropy, temperature, and E cell. Right? That's like almost all of our entire semester we're trying to pull together. Because equilibrium constant also is related to our rate constants, forward and reverse rate constant. Right? So there's everything's being tied together. What that means is we need to be really efficient with the time that we have left. So we have 2 days in class left. Next Monday is exam 3, which is only going to cover the material since exam 2. So that's going to be a significant chunk. I wish that we had more time, but our final exam is Wednesday. So I guess the good thing is it'll be out of the way quick, right? And the final exam is, it only covers Gen Chem 2. So those are the topics you need to study. Granted, Gen Chem 1 material kind of plays into it a lot. But it is the typical ACS exam, 70 questions. You have the 2 hours to get it. Alright. So, with that said, we are going to start on activity 55, the POGO activity 55. So I want you to very, very, very carefully read that Model 1. We're only going to spend about 45 minutes completing almost this entire packet. We're going to leave the last page for practice on your own, and then I have some slides we're going to get into as well. So let's go ahead and get started on activity 55, read through that, and then we'll kind of touch base every once in a while. We have a lot of help today, so make sure to utilize your supplemental instructors and GAs. Oh, yeah. Did anyone grab activity 56? Raise your hand if you got both. Okay, if you don't trust yourself to bring, that's Wednesday's class. If you don't trust yourself to bring that Wednesday, leave it here with me and I'll bring it back. If you're 100% sure you'll bring it back to class Wednesday, 56, then you can, hold on to it. We're doing activity 55. I didn't realize I put both up there, sorry.
So number 1 is
Yes,
So it says
okay, now what does it tell you? So just rewrite this. So, my entropy now for what conditions is it favorable? Right. Now, and another thing for entropy favorable. Now, let's see that we go values for that. Right. So, it's asking us, is this
oh, I know. Okay.
Alright, so in about 2 minutes we're going to go question blank. Activity Resistivity 55. So remember, question 1 is only asking in reference to enthalpy, is it favorable? In reference to entropy, is it favorable? So you don't need any calculations. You just need to read that first paragraph and then fill out that table. Raise your hand if you need a couple more seconds to finish question 1. All right, please, everyone, finish question 1. If you have any questions, make sure ask those around you or the team.
So this one, I'm just saying like these are in the negatives and these are everything else is in the negatives. But I mean saying like
they're not
there's
specified.
not specified yet. Okay. So it would be
All right, everyone. I'm promising to try to get you as far as I can in these 2 days of class, so I'm going to be pushing the pace, all right? So how do we determine whether it's favorable according to enthalpy? All right, so at the very top it says enthalpy less than 0 is favorable. What else do we call that? A negative enthalpy is... What's nice and loud? Exothermic, okay? So which ones here are favorable? Just these two, right? So yes, yes. The other ones are not. It's a terrible N. All right. Say again, Josh? Okay, so entropy, increase in entropy is favored. So which ones are favored there, Josh?
Whatever ones you have yes, it's going to be the 2 no's and the rest are yeses.
Oh, so you're saying no, no, and then the rest are yeses. Okay? So you guys had pre-class quiz, you've done some stuff in lab, you've looked at entropy, enthalpy, and temperature and how those things fit together. So go ahead and flip to page 2 if you haven't already. Look at that table and look at what relationships they show. And you should have a really good idea even before you do it, which ones of those relationships actually relate to spontaneity of a reaction. So go ahead and complete stuff on page 2. Make sure you answer questions 2 and 3 first. That's going to be really important before you go into that table. Rewrite this equation and then try to figure out how this is.
Oh, how it's equal. Okay, I know that it's what happened to my well, just in case
All right, let's go ahead and talk through a lot of the stuff on page 2. Question number 2, is there any reaction in table 1, up here that we just went through, for which both the enthalpy and entropy factors are favorable? Are there any? Should probably be a chorus, but no, right? Not favored for both, not favored for both, not favored for both, not favored for both. All right, are there any, question number 3, are there any in which enthalpy and entropy are unfavored? Okay, so then what they're trying to say is that according to this, we look at the next table and we say that some are still favored. So it's a battle between the two, right? So on the next page you have delta H, T delta S, delta H minus T delta S, and K. So what I want you to think about is what would these signs have to be in order for the reaction always to be favorable, regardless of how you use them? What would the two signs have to be? What would the sign for delta H have to be? Negative, okay. And the sign for delta S would have to be positive. Okay? So if we had both of those, then regardless of the stuff we talked about on the next page, that reaction is always going to be favorable. On the converse, if we have the opposite signs, right, a positive delta H and a negative delta S, the reaction will always be unfavorable. And it's going to be really important to think about what that means. What does it mean by unfavored? It doesn't happen spontaneously, but what does happen spontaneously mean? Directionality is really important. What happens if we took this bottom reaction and flipped it and said, well, products go into reactants, reactants go into products? What would happen to this, Josh?
I have a question. Isn't it already doing that with the arrows, though?
It's saying that this reaction is reversible, but these values of delta H and delta S are only for the reaction going that direction.
So then I don't know.
So then, Austin, what happens if we say, well, what about the reverse reaction? What if we flip this around? What would happen? That's it. Flip the signs. I like how Austin was like about to answer, and then the chorus came up underneath. All right, so then all of those things change, right? The entropy, instead of increasing, what would it be? I don't know. Anyway, we flip signs of everything, and then we end up with the reverse of that happening. So going back to Josh's, I think it's Josh's definition of what is spontaneous and not spontaneous. Spontaneous is in the direction that is written. Spontaneous means it's going to be going that way. So let's take a look at the next table. What is the K value going to be if the reaction favors products? You remember your K values, right? Concentration of products over reactants? Right? So K is coming back. We need that over and over again. So go ahead and answer everything from Model 2. Look at that table. Which of those relationships are product favored? Remember what K means and what those relationships mean. All right, so go ahead and finish the second page. And if you're done, move on to the third.
Well, guess what? I'm not.
If this is 0, then you can move this over to the other side. Here it's positive. So, and then think about the value of K. Really important to go back and think about what delta T is not. What is that little 0?
That's in the zero stage.
Now we know that for K is larger than 1, negative, K is less than 1, so therefore, yes, think about it.
And you're doing a great job.
I was like, you stopped.
That was
All right, so let's go ahead and get through page 2. So according to the values of the equilibrium constant, which ones appear to be products favored? What are we looking for there for products favored? Lindsay? Say again? Yes. Higher than what? Great. So if we're just saying specifically product favored, right? Favorable in the direction that we're written. The directionality is almost one of the most important things right now, because if we talk about the reaction in the other direction, we're going to have to do a lot of other steps, right? So which ones are most favorable? K is greater than 1. We have our top 3. And then which of the other columns gives us that insight? You guys did this in lab, right? Julia? All right, so the third column here, delta H minus T delta S. And what about that column relates directly to our equilibrium constant? Jonathan?
I mean, that is delta H on its own. And so if K is greater than 1, that delta G, or the equation that it has listed there, is going to be negative, and if K is less than 1, it's going to be positive.
Great, so I like how you kind of threw in subtly there that this column is, where is a good place to put it? This is delta G, but more specifically, delta G naught. What does that not mean? Standard condition. What's really important about standard conditions? Temperature, pressure, but the most important factor is concentration. What concentration does everything have at standard conditions? Molar, great. Molarity is important, right? Molality, not percent, mass, whatever. All right, so everything is 1 molar, and then they basically say, well, we're going to compare how likely all these reactions to go. If everything's 1 molar, this is 1 molar, that's 1 molar, that's 1 molar, that's 1 molar. Most of our reactions don't happen in 1 molar concentration. All right, so Wednesday's class, we're going to talk about what does that mean when we don't have a 1 molar concentration. We'll do a little bit of that at the end of class today as well, but that's what your pre-class quiz is for Wednesday. Okay, so delta G naught, if that value is less than 0, then we have a K that is greater than 1. All right, what's another way to say that? Product favored, reactant favored. What are we saying?
Product favored.
Product favored, negative delta G, the minimum of the Gibbs free energy diagram. Do you guys remember those? Who remembers Gibbs free energy diagrams? So if we have a negative Gibbs free energy, delta G naught, what does that look like? Go ahead and draw your Gibbs free energy diagram. So right now, go ahead and draw yourself one of these guys. And I want you to draw, what is delta G naught is negative, less than 0? What does that look like? What would your Gibbs free energy diagram, what properties would it have? Peter, can I ask you a favor? Can you go grab the things I printed off right before class? Off the printer? What's up?
Dr. Bailey. It's ugly, but that's where it is.
All right. What do you guys think? Here's a drawing. Here's a potential. Does this seem reasonable? Does it seem not reasonable? Clear off that little line right there, so we only go to the end. So how would you describe what's been drawn here? Is this reactant favored or product favored? This is product favored. Remember, equilibrium constant is at the minimum of the energy diagram. That if we are at any other mixture, let's say we only have reactants, we're going to be up here, we're at higher energy. In order to get to equilibrium, the ball rolls downhill. Okay, so this is drawn as product favored. The most stable mixture is mostly products. What do you guys think? Is that reasonable? Delta G naught is spontaneous. So let's go back to that idea for a second. I said that if we want to do this right, we really need to think about the directionality of the reaction. What does delta G naught less than 0 mean again? K is greater than 1. Great. Which means that it is product favored. So that's right. What else does a negative delta G naught mean? Ruby?
It means the products have less energy than the reactants do.
Say again, the products.
They have less energy than the reactants.
Well, so I would be careful about energonic versus endothermic exothermic. Let's not go there specifically. So typically when we talk about a negative Gibbs free energy and we talk about spontaneity, what do we say? Is the reaction spontaneous or non-spontaneous? And I'm going to add here a really important qualifier. Sorry, I ran out of room. What do I mean by in the forward direction? The way that the arrow is written from left to right. So if we change our definition of what's a product and what's a reactant, then this whole image flips over. We talked about that a little bit before. So the way that this particular reaction is talked about here in front of us is there's a mixture that is more stable when it has more products and reactants, which we can tell from our equilibrium constant. So then what is this standard conditions? Why do we care about standard conditions? How does that relate to the drawing of this? Matt?
A higher temperature is going to put more energy into the system.
So this actually will change if we change the temperature. So no. Because our delta G value depends on what our enthalpy and our entropy are, right? So those are not included at all in this diagram. So if we are looking at this particular diagram, what was the most important thing I said about standard conditions just a second ago? Concentration of everything is 1 molar. That means that all the concentrations are the same. That's our Q value. Where would I put that Q on this graph? Is Q up here at the very far left? That's all reactions, right? Would the Q be all the way over here? Where's it going to be? On the line, right in the middle. So here's the really cool thing about Gibbs free energy at standard conditions, is it simplifies the heck out of this, and it says that this is Q. From a concentration of everything being 1 molar, we know we can automatically draw this graph, because we know the sign of Gibbs free energy. To get from here to equilibrium, does the reaction proceed forward, backward, or not at all? The reaction has to proceed to our equilibrium constant, which is on the right. So the reaction proceeds forward. Negative delta G means spontaneous in that direction. So as soon as we know the sign of delta G naught, something we can look up in the table, we can draw this right away. And we know it's product favored. We know that the equilibrium constant is more product than reaction. You guys see the connections? All right. That is tangential to Gibbs free energy at different temperatures. All right. So if we go back to our activity, can someone describe question number 8? What is the qualitative relationship between the value of the factor identified in CTQ5, which we determined was this third column? What's the value between that and the magnitude of K? Brianna?
Inverse relationship.
How so?
So as delta G increases, K is going to decrease, or vice versa.
Okay, great. So as one gets bigger, the other gets smaller. But it's specifically, what about the sign? So as one becomes more negative, I would say,
Okay.
the other becomes larger. Right, so all three of these have a K greater than 1. And the one with the biggest, delta G naught, has a massive equilibrium constant. And the other ones, once you have a positive delta G naught, it's going to be a number between 1 and 0. It gets smaller the more positive that gets. All right, we're going to spend a couple minutes on this last Model 3. And then everything, if you have gotten to the exercises, these values, when it says look them up in a table, that's in the appendix of the PDF that is posted on Blackboard. So if you work on this and practice this, you're going to want to look up the whole PDF and look at those values in the table. I think appendix 1 or 2 or 3 or something like that. So let's go ahead and complete Model 3 real quick.
So, 0. Check out the key values. Yeah. You ready to finish up this microphone?
Yeah.
Logan, I think that you have something in that stack, not that one.
And one of these, it's right there. Oh, I got a few things. Oh. Oh.
Just the one is.
I know this one. My boyfriend does
Like if I'm on, like you have the other girls that are I don't know. No, I don't know. You know how you across all the other girls? My kids
No,
That's exactly what she's placing friends over.
That's what I mean. Doesn't matter. It doesn't matter. Yeah, so
You know what I mean?
My equation is I have CU plus C.
I deleted my old Facebook to get rid of all the American pictures I took, and then I realized I was tagged in super late.
All right, so let's hit these up real quick. For chemical reaction with a K greater than 1, is delta G naught positive or negative? Negative. We're favoring products, right? That one that we showed, the Gibbs free energy diagram, the minimums to the right of the middle. And remember, all of these are talking about standard conditions. So that standard condition means that our Q is 1, right in the middle. We're comparing it to K that's to the right. All right, and then for chemical reactions with K less than 1, delta G naught is positive. So that means when we have a K of 1, what does that mean for delta G naught? All right. So it's kind of what the next question gets at, in that it says, if we have delta G naught, remember, standard conditions, Q is equal to 1. If that means that the reaction, when we're at Q equals 1, does not favor products, does not favor reactants, that means that our Gibbs free energy diagram would have the minimum in the middle. Because we're always going to say that our Gibbs free energy is saying from this point, with Q equal to 1, does the reaction proceed towards products, negative delta G, towards reactants, positive delta G, or if it's already at the minimum, then we can go ahead and say that that's at equilibrium, Q equals K, delta G equals 0. All right? But kind of getting to one of Matt's points, does delta G naught tell us anything about entropy, enthalpy, and temperature?
It's equal to it.
Delta G naught is equal to it at standard temperature. But one of the things that's hidden there that we don't know unless we know more about the reaction is whether delta H is positive or negative. Delta S is positive or negative. And as we change the temperature, so if we scroll down to that last question, how do we get to this statement in question number 11? Delta H naught equals T delta S naught? Say again? 1 what? Is that what delta G naught is?
Yeah.
So in order to get to this, delta G naught has to be 0. Which means that our K value is, so that means our K is 1 because our minimum's right in the middle. And so one of the things that I want you to think about is, if you increase the temperature, is the sign of delta S, is this going to stay true if we increase the temperature?
No.
Delta H is going to stay the same, but this side is going to change. So all reactions have, think about the plot, temperature versus delta G, right? Josh, you have a question?
Yeah. You were just showing that if delta H naught is equal to temperature delta S, and you change temperature, then H would have to change too if it's still equal.
Nope, but we're no longer standard temperature pressure.
But if you're saying it's still equal, then something...
But we can't.
Okay.
It's not equal anymore.
Okay.
It's only equal if we have a K value of 1 when we're in standard conditions. All right, so have you guys seen a plot of temperature and how Gibbs free energy changes with temperature?
Nope.
So there are if we had a plot like this, that as temperature increases, Gibbs free energy increases, what is the sign of delta H? What is the sign of delta S for this reaction? Talk to your neighbor and see if you can figure that out.
Picture that you have.
From this drawing, from this graph right here, if I'm describing a reaction and I check Gibbs free energy at multiple temperatures and I find this, what do you know about the signs of delta H and delta S? And it's going to be useful to use this equation.
Yes.
We have a graph of and delta S to be negative, right? The negative sign. S to be negative.
All right, does anyone have some guesses? The signs of delta H and delta S. Logan, what are you thinking?
I'm going to say we said earlier where they were both favorable, so delta H would be negative and delta S would be positive.
Okay, if that's the case, even at 0 degrees Kelvin, wouldn't the reaction be favorable? Wouldn't it be favorable at really high temperatures too? Is that true here? Is the reaction always favorable here? Okay, up to a certain temperature, it's favorable, right? Then we get to a temperature which is not favorable in either direction, and then we get to where it's favorable only in the reverse direction. So I don't think it can be favorable for both of them, otherwise temperature would be irrelevant. Temperature plays a role here, right? As it gets warmer, does this become more or less favorable? So as T goes up, we get less favorable. So then, what does that mean? What does that mean about our signs?
So would they both be positive since changing S is dependent on temperature? And both are not favorable, so H has to be positive.
So if H is positive, and we're subtracting a really small number times a positive, then this is probably all going to start out positive, right? Do we start out positive? Okay. Matt?
Delta H has to be positive and delta S has to be negative.
Why?
Because that way, as temperature increases, you're actually adding, you're increasing the delta G.
So if entropy is unfavorable, right, negative, the warmer it gets, the bigger an impact that has on it, making it less and less favorable. Right? As temperature increases, we're making this less and less and less favorable. So that means to start out with, we're favorable when entropy really doesn't contribute. We just have a negative delta H, which contributes mostly to our Gibbs free energy. As we warm it up, entropy starts playing more and more of a role. Minus, negative, means that we're adding to it, which means that it's going to get less and less favorable until a point where at a certain temperature, this reaction isn't favorable in either direction, and past that temperature it becomes favorable in the reverse direction. All right, so you might see a few different plots of this. I do believe that the ACS final exam does have this type of a question in it, where it asks you about the sign of, it gives you either a sign of delta S and delta H, and saying is this always spontaneous, never spontaneous, or only a certain above or below certain temperatures. So if you don't have your head wrapped around how the magnitude of these influence each other and how that influences Gibbs free energy, then that's something you probably want to spend some time with.
Don't we want delta G to be negative?
So it's not about what we want,
Or not want, like,
but a reaction that's favored to go the way we wrote it would have a negative delta G.
so why wouldn't we want T to be bigger, because then that's going to make entropy larger, which is going to make G more negative.
Go back to the very first page, remember? What is a favorable entropy? Is it positive or negative? So, as entropy increases, it's more and more favorable. What this is saying is that if this is more favorable, if it's a positive delta S, that means that as it warms up, we're going to get more negative for Gibbs free energy. Does that make sense? So, if this is a positive value, the warmer it is, this has more of an effect on being negative, which is a spontaneous Gibbs free energy, like you're saying. However, if we have a negative entropy, if it actually is unfavorable entropy-wise, then the bigger temperature is, the less favorable the reaction becomes, because a negative and a negative is a positive, which means this becomes more positive. It really is all about mathematical relationships, so sit down and try to work through some problems like this and discuss, like, if the temperature goes up, how does that influence this? Try plugging in some numbers.
So
Try.
temperature is only, like, increasing is only less favorable if delta S is negative?
Correct. William?
Is it wrong to think about it as like as you add more temperature to the system, it's being more absorbed?
That is wrong. And the reason why is because you could turn the reaction around and the reaction is creating less in the directions favored. So spontaneity isn't always, it's about both factors. So as it warms up, if the reaction at warmer temperatures is favoring more dispersion, more disorder, then that's going to be a positive delta S, which means it's going to contribute in the way that makes the reaction more spontaneous. So you need to really think about each individual component and how they fit together. All right, so we're going to switch gears. Are there any more questions on this before I move on? Ruby. So in this one, we'd have to have a negative delta H because when temperature is really low, this is the only thing that contributes to our Gibbs free energy, and we know our Gibbs free energy is negative to start with. So this is less than 0, and this is, wait, did we say that? So H had to be negative. They were both negative. Right? Because when we start out, the only contributing factor is delta H, really. And we're negative. Gibbs. As it warms up, it becomes less spontaneous, which means that this has to add to it, so negative and a negative. Yes, I didn't specify here, but if we started at 0, then the contribution of entropy would be 0. Correct. Can we get everyone? Sorry, I have a lot of side conversations. Savannah?
How does this graph assume that delta S is negative?
So if we start with 0 temperature, this whole side is blocked off, right? So that means that the sign of Gibbs free energy is directly proportional to entropy. As we warm it up, now this begins to contribute. We know that the Gibbs free energy becomes bigger and bigger, or more and more positive. That only happens if this is negative. That negative times a negative is a positive. So the bigger this gets, the bigger the influence of entropy is. All right. We are going to switch gears, and we're going to work on the worksheet that I handed out. So let's just go ahead. We're going to go high pace, right? We got 25 minutes left of class. So let's hit it. Hit the ground running. All right, we're doing the single sheet of paper that I handed out. Questions on the screen.
Focus.
Please. A couple more seconds. We have a 2-to-1 response. I want you to convince your neighbor which answer is correct and make sure you describe why. The reaction to be spontaneous in the reverse direction. All right, Manu, which one did your group choose and why? Why'd you choose A? And after deliberation, we went from 2-to-1 to you all convincing your neighbors. All right. So that just means that at whatever point you're at, if you have a positive Gibbs free energy, the reaction is not spontaneous in the forward direction. In fact, it is only spontaneous in the reverse. So which of these is true when the reaction has reached equilibrium? All right, closing out. Matt, which one did your group decide is the reaction at equilibrium?
Isn't it? B.
Why?
Well, I think, because from what I was doing before, if it's at more than 0, it's going to be positive, and if it's less than 0, it's going to be negative. So I just deducted that B would be equilibrium.
Fair. Anyone want to add to that, Christina?
I mean, it's not product or reactive favored, but it doesn't lean either direction. So.
Great. So the last paper kind of talked about product favored, reactant favored, K being less than or equal to 1. But this is not talking about standard conditions, right? So there's this equation that we're going to be using today. Bringing it all together. All right. When we're at equilibrium, how do Q and K relate to each other? Ask your neighbor. How do Q and K relate to each other at equilibrium? We're not talking about standard conditions. We're saying when we get to equilibrium, how does Q and K relate? All right, I didn't hear a lot of conversation, so maybe you guys just all got that right off the bat. Tripty, how do those two values relate when you're at equilibrium? At equilibrium, that's kind of our definition. That we know there is the most stable mixture wherever that mixture is, right? And when our actual mixture, Q, has gotten to the most stable mixture, that's when we've reached equilibrium. So that's kind of what I want for the last 15, 20 minutes of class to think about, is that Gibbs free energy diagram. Where is the minimum? And then where are we compared to that? And that's going to determine what our sign is. So this, not at standard conditions, means that our Q can be anything. We are going to go back for a minute and talk about at standard conditions when Q equals 1. And that's we're going to try to compare those two. So in this equation right here, what happens to the equation when Q is equal to K?
That log
natural log of 1 is 0. RT times 0, 0. Okay? What if the top part? If it is spontaneous in the reverse direction, what does that mean for Q versus K? Talk to your friends. What is Q compared to K if the reaction is spontaneous in the reverse direction? All right, I'm going to draw a Gibbs free energy diagram. You guys might love it, you might hate it. Let's not do that, actually. All right, I have a Gibbs free energy diagram here. Can I, on this, generate a scenario in which the reaction is favored in the reverse direction, where we have a delta G that's positive? Can I describe with this reaction as it's drawn right here, can I describe a way in which we'd have a reaction that would fulfill that last statement? That the reaction is going to tend towards more reactants to reach equilibrium. That we have a positive delta G. I'm not saying the reverse reaction, I'm saying this reaction. Is there any possible Q value? Remember, we're not at standard conditions now. What Q value could we have to make this reaction go in the reverse direction? Hello? Q is greater than K. So, where would that be on this graph? Where would a point on that line be if Q is greater than K?
Say Gibbs free, and that's always in the middle.
Standard conditions is always compared to the middle, but I'm saying we don't have to have that Q of 1. If we have any Q value we want, we could do an enormous Q value and be right here. You guys see how Q is bigger than K right here? This is our equilibrium. Here's our actual Q value. In order for this reaction, this Q value, to reach equilibrium, it has to proceed in the reverse direction. What's delta G for that X, that Q value right here? Is it positive, negative, or 0? If we go back and we use this equation that I have kind of written here, delta G equals RT ln Q over K. Is Q bigger than K here, or is Q smaller than K? Q is bigger than K. So what does that make this fraction? Top is bigger than the bottom. That means it's bigger than 1. If we take the natural log of a number bigger than 1, is it positive or negative? ln of a number that's greater than 1? It's positive. So, anytime Q is bigger than K, ln of that number is going to be positive. R is a constant, it's a positive value. Temperature is Kelvin, always positive. Delta G is going to be what sign? You guys seen these relationships? I think I have like 4 people on board, and I might have lost everyone else. All right, so I hesitate a little bit to go forward because we're going to, there's 2 scenarios we can talk about, right? There's any Q you want, and talking about that relative to K, which is what we've been talking about here. And then there's, at standard conditions, what does that look like? So let's transition back to standard conditions. On this graph, if I were to describe Gibbs free energy at standard conditions, what would my sign there be? Talk to your neighbor. What would the sign of Gibbs free energy at standard conditions be for this graph, for this reaction? Start out by saying, where is Q if we're at standard conditions? All right. So how are we thinking through this? Can I have someone talk through how we would determine the sign of Gibbs free energy at standard conditions for this graph? Nice and loud, Logan?
So it's in relation to like the center, right?
So relationship to Q equals 1, which is right there, right? So compared to that point, how do we determine Gibbs free energy sign?
It's like the ball going downhill, so it goes toward product.
So what does that mean? Is that Gibbs free energy being positive, negative?
Negative.
Absolutely agree. So remember that the key to this, the way to untangle this if you're getting confused, is if we're looking at a table in the back of a book, they have measured everything at standard conditions or calculated it, but it's a reference point. It's saying if everything is 1 molar at standard temperature, is that reaction product favored, which is a negative delta G naught? Is it reactant favored, positive delta G naught? Or is the Gibbs free energy diagram showing a minimum close to the center, which are going to have almost a 0 value for delta G naught, only at standard conditions? The questions I was asking here, with this green to X, these aren't at standard conditions, right? Because most reactions aren't at 1 molar. So we can look at this reaction, and we can draw this diagram because we know delta G naught is less than 1. And then we can say, but if I start with almost all products, I know that reaction is going to go in reverse to get to equilibrium. Or I could say, if I start with all products, which way is it going to go? All products, all the way up here, it's going to go that way. And the magnitude of that change from top to bottom, that's our delta G. That's the magnitude of the delta G. The sign goes left, positive. The magnitude of it's how far the drop is. All right, so let's go through the rest of these questions I have. And the learning objectives are, for this last part, you guys got the earlier part, yeah, you're good. I want you to be able to predict a spontaneous reaction by comparing Q versus K, and that equation might help you mathematically confirm what we talk about. So that means that you need to be really comfortable with thinking about standard conditions and most of reality, which is non-standard conditions. And we're going to talk on Wednesday about how to convert between those two. Interesting. We're going to draw the Gibbs free energy diagram just from the sign of Gibbs free energy at standard conditions. And next class, we're going to be looking at how we can use these Gibbs free energy values and signs to talk about driving non-spontaneous reactions forward. Our bodies make ATP all the time. That is not a spontaneous reaction. So how is it that our body is able to drive the generation of ATP? And that's by coupling with a whole bunch of other reactions that are spontaneous in the forward direction, driving that one in the reverse direction. All right? So let's just get on the same page with terms. Which one are we going to go ahead and call? So most people are saying that B is exergonic. I agree. So the definition of exergonic is that it releases energy over the course of the reaction. What I don't like about these diagrams is it tends to show that at the end we just stop. Right? This is not a great Gibbs free energy diagram. So I would like to see a Gibbs free energy diagram where it starts at Q on one side, ends up at K, and then we have it go up again at a certain point, because K is never infinity like this. If we take this all the way back to kinetics, which part of this graph, are you guys comfortable if you had a graph like this saying which part is kinetic and which is equilibrium phase if it wasn't written on the screen?
Just like this, yeah.
So what's the difference? Why is one side kinetic and one is equilibrium? Define it to your neighbors. Come up with a clear, concise definition, and don't throw misconceptions in there. Shanidra, do you have a good group definition you want to share with us? Marina? So I think this might be this type of question about differentiating between equilibrium and kinetics. Some variant of this is something you can expect on an exam. Like having a really crisp definition, differentiating between what's different between kinetic region and equilibrium region of a graph. Looking at examples of them, those kinds of things are really important. Colin, what are your thoughts?
I was just thinking that kinetic phase, there's net change, and then equilibrium phase, there's no net change.
Great. What can we add to that? So there's no net change in concentrations, I would say, of reactants and products once we get to equilibrium. What else can we add to that? What are some more specifics of the difference between equilibrium part of a reaction versus the kinetic part of a reaction? Kinetic phase. What are some of the most important characteristics that we define happen here and either are still happening here or don't happen here? What's that? Does that happen in both? Only in one? So say it as a sentence then.
So you use up reactants to make products in both phases.
Fantastic. Does everyone remember that? All right. The big misconception a lot of people wrap into this part of the class after they've gone through it a bunch is, oh, in equilibrium, the reaction stops. All right. So Colin hit on it. There's no net change. Implied in that is that there's still change, constant change, but it's the same being used up and produced in both sides. So it looks like there's no change happening. All right. That's one of the main points I want to drive home. So in the left side of the reaction, it's kinetic phase. We're thinking about the reaction rates, how concentrations are changing. On the right side, we're saying, well, what happens if we perturb this? How is it going to get back to those concentrations that described by K? On the left side, we're not at equilibrium. In this particular case, because our reactants are being consumed and our products are being formed, we have a negative Gibbs free energy. What's the Gibbs free energy on the right side of this graph? We're at equilibrium, delta G equals 0. All right? Draw out a Gibbs free energy diagram, please. So for these three questions, I want you to take each of those three graphs, and for each of the three graphs, draw one of the three examples, right? Question 6, 7, and 8, use one of those three graphs for each of those examples. Draw a K in all three of those graphs. Put where Q would be for each one. Specify question 6, 7, and 8. and put Q in the appropriate place with an X. All right, we have a 2-to-1 answer on this. Q is larger than K. So in all of these graphs, and I think, I might give it away. No, okay. Q is larger than K. First, let's define where K is on this graph. Ruby, can you put X where K is? Okay, does everyone agree that that's K? K greater or less than 1 here? We have a favored reactant, favored reaction. That means that K is less than 1. So, in this particular question, we're saying Q is larger than K. So where are we going to put Q? Is this question 7 for you guys? I think this is question 7, not 6. So where is that? Where are we going to put Q? Right or left or on the X? We're going to put it anywhere out to the right of K. Because remember, this is concentration of products over concentration of reactants. If that number is bigger, it's going to be further towards products of the reaction. So if that's the case, in order for this reaction at this starting point, any starting point over here, to reach equilibrium, right, what can we say about the spontaneity of the reaction? Is it spontaneous in one direction or the other? Are we at equilibrium right now?
No.
No. So it's spontaneous. Which direction? This direction or that direction? Point. Towards reactants. What does that mean about the sign of Gibbs free energy? It's non-spontaneous in the direction written, meaning that our Gibbs free energy for that Q and this K is greater than 0. All right? So that's what I wanted you guys to do for each of these 3. And this is where we'll start next class, looking at how to disassemble this equation and use math to support what we just drew graphically. All right, pre-class quiz should help you a little bit, but I want you picturing those Gibbs free energy diagrams. If you're really confused about this, stick around after class, come ask some questions. I'll be here until you guys stop asking questions.